Hi everyone, I'm Ryosei Tamura from Carnegie University, and this summer I worked in the Momentum Robotics lab under Professor Jeffrey Ignovsky. Today I'm going to talk about multi-modal demonstrations for dexterous manipulation. We want robots to do cool stuff. On one side, we have robots doing long horizon tasks like cooking shrimps or tying shoelaces. On the other hand, we have contact-rich manipulations like in-hand rotation or spinning a pen. I'm impressed by each of these alone. But what really fascinates me is the combination contact rich dexterity in the middle of a long horizon task. So, the goal of this project is to teach robots long horizon, contact rich tasks from real world demonstrations. So, how do you actually demonstrate a long horizon or contact rich tasks? There are two standard ways. The first one is teleoperation. Teleoperation is when the operator drives the robot remotely with a remote control. This time, I used a space mouse for the X arm and hand retargeting for the leap hand. This covers the long horizon of the task well, but it is imprecise for fine-grained contact, since it is hard, since you don't have the tactile feedback and the retargeting isn't accurate enough. Kinesthetic teaching is when human physically guides the robot's fingers directly. This excels at the contact-rich part, since there's no interface between me and the robot, and it is intuitively easier to control. But it's physically exhausting when you want to collect lots of data for a long horizon task. The best prior work has pushed each modality separately. ResPilot made teleoperation much better. They use a learned residual on top of retargeting, good for teleoperated finger gating, but it's still a map from the human hand to the robot's joints. The robot can only reach configurations a human hand can produce. Kindex showed what kinesthetic teaching uniquely offers. With the operator wearing the robot hand, the demonstrations capture real contact forces. Since they kinesthetically teach, they paint the human hands out of the images. The fingers are strapped on the operator's hands, so again, the robot inherits human kinematics. Both bind the robot to human hand kinematics. So we aim to mold the fingers directly and to utilize the robot's full kinematics range. Here's our pipeline. It combines the two modalities. First, we collect teleoperation demonstrations for the whole task, and then we train an image-based diffusion policy by behavior cloning. During the closed loop rollout on the real robot, it can handle the long horizon structure, but it fails at the contact-rich moments. This is when I kinesthetically align them in real time. Those corrections go back into training in a dagger-style loop. To train a diffusion policy on both kinds of demonstrations, we first have to overcome a training deployment gap. The left image is an image during training. It has a human hand in the frame during the kinesthetic teaching. However, on the right, it is an image during deployment, and it has no hands. An image-based policy trained on the left will build features that depend on my hands because they're large, salient, and correlated with emotion. However, at deployment, those features get nothing. The policy fails even though the motion supervision was correct. This is the hand visibility gap. There are two existing ways to fix this, and each trades one problem for another. The first one is mask the input at test time. Segment every frame and let only object pixels through. Making masks offline can create very clean masks, but during deployment, the masks become inconsistent, which eventually results to out of distribution. The second option is in paint the human away, like Kindex. But during kinesthetic teaching, my hands cover most of the scene, so the inpainter has to hallucinate what's behind them. You can see the smudging on the right side of the image. And these artifact-ridden frames no longer match the clean images the robot sees at deployment. Our approach doesn't edit the image but supervises the encoder. The raw image directly goes into the ResNet 18. Its features feed the diffusion policy as usual, through attention pooling. But we add a second auxiliary head, which is a small segmentation head that must predict the object mask. The lost is just the diffusion policy loss plus a weighted binary cross entropy on predicted masks and the target masks that was made offline using SAM3. The predicted to predict the object mask, the encoder is forced to represent where the object is and its features get steered toward the cube instead of the operator's hands. During deployment, the seg head is thrown away and the raw image goes straight in without a masked image or impeded image. We visualized where each policy's encoder attends using GradCam. GradCam is a gradient-based attribution method. It explains a scalar output of the network in terms of the spatial feature maps of its last convolutional layer. It shows us which regions of the image does the output depend on. Standard GradCam explains a class score. A diffusion policy has none, so we define the target scalar as the L2 norm of the predicted action chunk, a measure of how strongly the policy intends to move. The saliency map then tells us which parts of the image that intention depends on. As you can see, the impended policy and the mask policy, the saliency lands on the same place through sequence of frames. The image contribution, is little, and the policy learns on proprioception. However, the current method, the saliency maps concentrates on the cube and the robot hand. For the future work, first, I will push invariance further. Explicitly train the encoder to produce the same features for an image with hands and the same scene without them. Secondly, I will build a self-improving pipeline. I will incorporate kinesthetic teaching into the rollouts that are trained with teleoperation demos. Third, I'll compare the combined demonstration policy against a policy trained only on teleoperation data. Acknowledgements. As part of the support of SoftBank Group Corp. And ARM, I was able to participate in the Robotics Institute Summer Scholar. I would like to thank Rachel Burson and Dr. John M. Dolan for directing this. I would also like to thank Uksang Yo, Yumin Mao, Professor Jeffrey Iknovsky, and my fellow lab mates for their mentorship and guidance. Thank you.